Good afternoon. Thank you for joining us at this conference. We are very glad to present you a very exciting work that we have been done in this project, which we call GstCUDA, Easy GStreamer and CUDA integration. But first, let me introduce myself. I am Daniel Garbanzo, and along with me on the stage, we have Michael Gruner. We are both embedded software engineers at RidgeRun. There is the agenda of the presentation. First, we will give you a short brief about RidgeRun. Then we will be giving an overview about GStreamer and CUDA, so we can explain what the GstCUDA means, and also show you the capabilities and the cool stuff you can do with that by showing you some application examples, and also we will show you some performance statistics, and hopefully we could run a GstCUDA live demo on a Jetson TX2 that I have right there. Finally, I will close the session with a Q&A section. So let's talk about RidgeRun. We are a US company located in Costa Rica, so all the customers love to visit us. We have over 10 years of experience in embedded Linux. We do a lot of work on the kernel, camera drivers, GStreamer, servers. Also, we work a lot on open source development, and more important for this event, also we work on artificial intelligence and system optimization on a bunch of different frameworks like GStreamer, CUDA, OpenCL, OpenGL. Today's presentation is to show you some of the cool stuff that we have done with GStreamer and CUDA.
Thank you, Daniel. So I think it's safe to assume that everyone here has access to a digital camera. I actually think it's safe to assume that everyone in this conference has access to a digital camera. And that's because simply multimedia is everywhere, right? Just to give you an example, we just read an article on Forbes that said that home security cameras will double from 54 million units to 120 million units by 2023. To give you an idea, 120 million is roughly the amount of kilometers we are away from the sun. So it's pretty amazing. That represents almost a 10 billion market on the US on home security cameras, not to count any other camera, right? So our homes have cameras, our cars have cameras, our drones have cameras, our doctors, our mechanics, everyone wants or needs a camera. So until a few years ago, the cameras captured those images for a human to enjoy or to analyze or to even make a decision based on it. But a few years ago, starting from a few years ago, and take this conference as an example, now these cameras are feeding autonomous systems where no humans are even involved. Take, for example, self-driving cars. Take, for example, smart locks, delivery robots. No human is even involved. And, well, don't get me wrong, that's an amazing thing. But as cameras get smarter and smarter, we start needing more processing resources. So on the one hand, everyone wants a camera. That's where GStreamer will come in handy. And on the other hand, as cameras get smarter and smarter, we need more processing resources, and there's where CUDA will be helpful. So for those of us who are not familiar with GStreamer, well, GStreamer is a multimedia framework to handle mostly audio and video. Actually, you can handle whatever you want with GStreamer, but you will see it being used mostly for audio and video. It's open source. We love that about GStreamer. And even though it's open source, the documentation, the online support is great, which is rarely seen in open source projects, but those guys are amazing. The reason why RidgeRun loves GStreamer so much is that GStreamer by design is modular, portable, and flexible. I've seen GStreamer running smoothly on small platforms such as the Raspberry Pi, for example. And when I say smoothly, it's really smooth on the Raspberry Pi, or even handling thousands of customers on a huge server farm. So really, GStreamer is portable and flexible. So GStreamer is engineered in a pipeline architecture, right? So inside the pipeline, we have these small processing blocks, which we call the GStreamer elements. Each GStreamer element handles a different processing task in the pipeline. So think about, for example, encoding, filtering, scaling, whatever the pipeline needs, each one is represented by a processing unit. So for example, in this example, this is what I want you to take from this slide is that building multimedia applications with GStreamer is pretty much like playing with Legos, right? In order to build a different structure, you would arrange the different Legos in different kinds of ways to build different buildings. It's similar with GStreamer and multimedia applications. For example, if you wanted to build a MP4 video playback application, well, you would use these elements. The first one is the file source, which will read the data from the disk, and then we will push that data to the MP4 demuxer. The demuxer, what it does is it parses the MP4 headers and splits the data into the video and audio content. So that video and audio needs to be decoded, right? So let's say for the sake of this example that we have H.264 encoded video and MP3 audio. So you push that encoded data to the respective decoders, and finally you run them using the video sync and the audio speakers, for example. Let's see for a moment this other application. This is a video recording application. So we start from the camera source that is represented again with a GStreamer element. Then let's say that you need to scale it and color space convert it. We have an element for that. Then we push that data into the encoder, and then we contain it into, I don't know, transport stream or MP4. And then finally, you write that data to the disk. So a very common question we get all the time, and to be honest with you, is a very valid question, is why do you like so much? What do you like so much about GStreamer? I mean, a trivial application like this, I can write a trivial application like this using other frameworks in less than 1,000 lines of code. I mean, let's say, for example, OpenCV. This can be fairly trivial with OpenCV. But let's assume that you write this for your customer, and all of a sudden he decides he wants to move to another platform. And this other platform has a hardware-accelerated encoder. And of course, your customer will want to use this hardware-accelerated encoder. So if you were to use GStreamer, ideally, it's just a matter of plugging out the software encoder element and plugging in the hardware encoder element. I'm not sure that's as trivial as with OpenCV. I mean, but for the sake of this discussion, let's assume that the customer requests another change, a bigger change. Now he says to you, hey, I don't want to record anymore. Now I want to do network streaming, and I want to receive the image with my phone, for example. Again, if you were to use GStreamer, you would only take out the file recording element, or file sync in GStreamer terms, and plug in the network streaming element. It's as simple as that, ideally, all right? I'm sure that's not a straightforward change. That's a very invasive change using any other framework. So that's why we love GStreamer that much, because it allows us to write applications for our customers that can be ported, that can be scaled to different architectures, maybe a different hardware, different cameras, different sensors easily. So we just save them tons of development time just by choosing the right tools from the very beginning. That's what we love about GStreamer. And there's a one-to-one correspondence with the code and the block diagrams that I'm showing you. So those strange syntax over there, that's the syntax equivalent with the block diagram. So you can literally take that and paste it into the terminal, and it will start a video recording. So on the one hand, GStreamer allows us flexible access to multimedia stuff. And on the other hand, what about heavy processing? That's where CUDA comes in, right? I know everyone here is familiar with CUDA, but if you're not, well, CUDA is a development environment that provides you with a lot of tools, drivers, libraries, everything you need in order to accelerate your application using the GPU. A few years ago, not that much ago, there were some algorithms that were impossible to run due to their sequential nature, right? They were impossible to run in real time, sorry. Thanks to CUDA, now we can run these algorithms in a parallel way using the hundreds of cores available in the GPU. So finally, these algorithms are able to run in real time. And if you have attended a lot of great talks about Insight tools and stuff, they also provide a lot of profilers, debuggers, a very complete suite of tools that will allow you to take the most out of your GPU. So we also like a lot CUDA. So as you may guess already, GstCUDA tries to combine both the GStreamer flexibility, all the multimedia handling, along with the power of NVIDIA CUDA. Actually, our main goal is for you as a developer to forget about writing any GStreamer code. We want you to focus on your algorithm. Your algorithm is what makes your product unique. It's what adds direct value to your product. So GstCUDA will take care of the multimedia part, and you take care of your algorithm, which is, again, what makes your product unique. Actually, you can even use GstCUDA, and that was our goal from the very beginning, without needing to know the GStreamer internals, without even knowing programming a single line of GStreamer, if you would. What does GstCUDA solve specifically? Well, the first and most straightforward are integration complexities. I mean, starting from the very beginning, you have the build system. You want to make sure that your CUDA algorithm is built along with the Gstreamer element all together in a single project. If you're writing, GStreamer is written in C, for example, and if you're writing C++ based CUDA, you need to take care of those bindings. And it starts getting complicated. For example, this is not a regular CUDA executable. It's not even an executable. You need to build your CUDA into a shared object, which you link against the GStreamer element, which in itself is another shared object. So it can get quite complicated, and GstCUDA handles that transparent for you. Because these things are complicated, and again, we want you to focus on the stuff that really matters, which is the algorithm. Let's take this data, for example. This is real data taken from our timesheet report archives. These are two projects that combine GStreamer with CUDA. The first one was before we conceived GstCUDA. We made everything from scratch. The second one is when we actually managed to leverage GstCUDA. We developed GstCUDA, and we could recycle all the code base that GstCUDA offers. So these were kind of small projects, but still, you can see that GstCUDA accelerates 10 times development times. And for this specific project, 10 times means 3 months that you could have invested in your algorithm, adding more value to your product, making your product smart. You don't need to waste your time on multimedia stuff that it's boilerplate code. Another important part that GstCUDA solves is memory management between GStreamer and CUDA. So if you are familiar with CUDA, you may know that there are a lot of different memory types. There's CPU memory, there's device memory, there's CPU pinned memory, unified memory, and they all serve a different purpose, and you want to optimize your application using whatever suits the best for you. And it's not as trivial as taking the data that GStreamer gives you, taking out the pointer and giving it to the GPU. It's not, that won't even work. I mean, there's work you need to do underneath. For example, we had a customer that had a big requirement on the Jetson TX2. He wanted to capture 2 4K streams at 60 frames per second. He wanted to run an algorithm on the GPU. So when we started developing that, our first approach was to take the CPU memory from GStreamer, allocate device memory, and do the CUDA mem copy. Using that approach on the TX2, we weren't able to even achieve 30 frames per second in a single stream, and the customer wanted 2 and at 60 frames per second. So then again, we invested a lot of time, a lot of research, a lot of investigation, reading a lot of material, and figuring out a way to integrate GStreamer and CUDA properly, making sure we are allocating the right kinds of memory, sharing the same memory against through the whole pipeline, so that we can, we can achieve a zero mem copy pipeline. That's what allowed us to finally get 4K streams at 60 frames per second, both processing on the GPU simultaneously. So again, we integrated that into GstCUDA, so the developers don't need to suffer with that anymore. That's all integrated and happens transparently within the GstCUDA framework.
So let's talk about the supported platforms. As RidgeRun is an embedded software-based company, we are focused on NVIDIA embedded platforms. GstCUDA is supported for all the Jetson family device portfolio from Jetson TX1, TX2, AGX Xavier, and also the most recently announced Jetson Nano that was released on the keynote of this year. Also, being this project a GPU-based project, we can straightforward port it to another architecture, for example, a desktop or servers that uses NVIDIA GPUs. So if you are interested in porting that framework, just tell us, and we will be happy to do that. Let me talk about the GstCUDA features. GstCUDA greatly simplifies the way a developer can add a CUDA algorithm into a GStreamer pipeline. Our project offers a set of quick prototyping elements that allows to easily load your algorithm.
I think you lost audio.
That easily allow your to load your algorithm into a GStreamer pipeline straight out of the box without the need to write any line of code. We give ultra-fine control of the image in all the aspects. For example, we give independent memory regions for each plane. Also, we have independent width, height, and strides for even each plane. We support all this flexibility because the CUDA algorithm could be adapted to the most complex and atypically hardware-accelerated elements that you could add to the pipeline, specifically for those NVIDIA platforms. So, and this facilitates the way that. Yeah. Also, GstCUDA manages all about the memory handling between GStreamer and CUDA. There is in an efficient and automatic way, so the user don't have to worry about how to handle the memory between those two frameworks. That all occurs under the hood, and the developer don't have to spend time on that. So, as you may know, on the Jetson developer platforms, there are too many hardware-accelerated modules. I don't have any phone here. Excuse me. As you may know, the Jetson platforms had hardware-accelerated modules for the capture and display subsystem for scalers, encoders, decoders, and color space converters. And those specific hardware modules handle a specific hardware memory buffers, and they are capable to share between them and take out the best of the performance of those boards. GstCUDA allows to directly access those hardware memory buffers by using low-level specialized APIs that are capable to map that hardware buffers and take out a pointer that is also accessible by the GPU. Also, for other type of configuration of pipelines, GstCUDA offers a unified memory allocator mechanism, which consists, for example, in that the previous elements in the pipeline will write the data into that unified memory allocated buffers, and then that data could be accessed also by the GPU and the CPU without an explicit memory copy. That way, to handle the memory provides a high-performance GStreamer and CUDA applications by ensuring a zero memory copy interface between CUDA and GStreamer. Let me go deeper on the framework. So let's talk more about the quick prototyping elements. Those elements that we offer are based on different topologies as the number of inputs and outputs. The specific reason that motivates us to create those elements are the workflow of developing a project. You start first developing and testing your algorithm, and this is an iterative process of trial and error. You need a lot of debug, so you don't need to waste time building and modifying the whole project. You just need to modify and build the CUDA algorithm, recompile it on each debugging iteration, and then the quick prototyping elements are capable to load the GstCUDA algorithms as a shared object or plugin on runtime. Also, this offers the possibility to change the algorithm on the fly. For example, you can allow your user to have a set of different algorithms for a specific purpose, and they can choose between the algorithm that is being implemented in the application. Here we have the most basic topology of our first quick prototyping element. In this case, we call that Cudafilter Element. As you may know, this is a similar concept as the NVIDIA filter. It has a single input, single output configuration. In this case, it has a camera video feed. The pipeline example that we are showing here has a simple camera video feed. And the Cudafilter element is loading a medium filter shared object CUDA algorithm, which are cleaning a salt pepper noise on the image that you can see on the last block. For example, let's think that you need to test different kernel sizes to test the performance of your CUDA algorithm. You just need to modify your algorithm by changing the kernel size, recompile the algorithm only, generate a newer shared object, and by changing the property location of the Cudafilter element, indicating where is the new shared object, and running again the pipeline, the Cudafilter element will load that algorithm and execute the new version of your algorithm. You don't spend any time on the integration. You don't need to write any line of code about the GStreamer or the whole application. And that speeds up the process a lot. There is the second element, in this case the Cudamux Element. It has a more complex topology, in this case multiple input, multiple output configuration. For this example, we have a RGB camera and a thermal camera as an input, and the algorithm that we are implementing consists on a thermal overlay. In this case, if the thermal camera pixels exceed some kind of threshold, we make a color mapping over the RGB input frames by accordingly to the configured threshold values. In this case, for example, this speeds the developing process a lot of the memory mapping configuration, because we just need to change some threshold values, recompile the shared object, and test again. So if we have to do that on a whole application and need to rebuild the whole application, we would lose a lot of time in that approach. With GstCUDA, using the Cudamux, we speed up the development process a lot. So let's speak, let me allow you to explain how to interface your algorithm with GstCUDA. We offer two kinds of interfaces, one from each element, the Cudafilter interface and the Cudamux interface. They are pretty same. The only difference is that the Cudamux interface allows several inputs. And as you can see, the open function will be called before the first frame will be processed on the GPU. So you can perform here some initialization routines. And the close function will be called after the last frame will be processed on the GPU. So you can clean up memory, doing some closure processing and stuff. And the process functions receives a GstCUDA data structure, which is the structure that we create to handle the data pointers to the memory and separate that data in different strides, in different planes, with assigned different strides and width and height for each plane. And as you may note, there is a process and a process IP. What is the difference between those? Process IP refers to processing in place. So the input buffer and the output buffer are the same. Every change that you make to the in the CUDA algorithm that changes the input image will affect the input buffer, and you don't need to allocate a new output buffer because the same input buffer is the same that is going to be out. In the case of the process, the normal process, the not in place, we need to allocate a new buffer for the output, and the input buffer remains untouched by the processing. In the case of the process in place, it presents a better performance. In some case of algorithms, for example, the thermal overlay, in that case, we only need to process a region or modify a region of the image, not all the image. In that case, by just writing the pixels that exceed the threshold, that is only a region of the whole image, we don't need to write to the output buffer the pixels that are not being modified by the algorithm. So that speeds up the processing time, and also we don't need to spend time by allocating an output buffer. But for example, not every algorithm could be executed by this way. For example, the common convolution filters need to perform some kind of linear combination between the neighbor pixels. So if you apply a processing in place, the data will be corrupted or modified, and you will will receive some unexpected behavior on the algorithm by performing a processing in that way. So let's imagine that we have a case that the quick prototyping elements do not meet the requirements of your project. So we also offer some kind of base classes that represents each of the topologies of the quick prototyping elements, one from the single input, single output, which is the GstCUDA base filter, and one for the multiple input, single output, which consists on the GstCUDA base meso class. In that case, we also provide some examples on how to use those classes to create a custom element, and also the quick prototyping elements are based on those classes. And this is an example of that. We have here an image stitching application. In that case, we couldn't use the Cudamux element because the output image is larger than the input images, and that exceeds the capabilities of the Cudamux element. So here we use a custom element based on the GstCUDA base meso class. So let's summarize what does the framework offers. It offers the GstCUDA API, which contains all the GStreamer unified memory allocators, the parent classes that I have mentioned, and all the required structures and functions and methods to handle all the memory interfaces. Also, we offer a set of quick prototyping elements to run easily and quickly your CUDA algorithms, and a set of examples to use straight out of the box with the quick prototyping elements and also with the parent classes. And here is a quick video that demonstrates or shows some example application that you could use with GstCUDA. Here is a border enhancement algorithm using a Sobol filter that may be used for industrial applications. These are just basic examples of how a bigger system or bigger application could use GstCUDA to accelerate or speed up the development process. Here we are applicating a hue transform to detect lines and circles on the GPU. And here we are implementing a motion estimation detection based on the NVIDIA's example. All that is being running on the GPU using GStreamer with the GstCUDA framework. I will leave the control to Michael to show you some performance statistics.
Thank you. So we first wanted to test our GstCUDA with a fixed image size but a varying algorithm. The reason for this is to stress compute capabilities and not data throughput. So for that, we tested a simple convolution. For those who are not familiar with the convolution, that's like the cornerstone algorithm for image processing. Many, if not all, of the filters are implemented or can be implemented using the convolution. So for this particular test, we are using the 1080p at 60 frames per second using our Cudafilter Element, using the unified memory allocator, and using the Jetson TX2 that we have right here. So first, the maximum frame rate that we could achieve with that. First, a disclaimer. This is a very naive convolution implementation. We did not spend any time optimizing the convolution because it's not our goal for this presentation. We just want to see if GstCUDA introduces significant overhead to the processing. So as you can see, on the top, we have the green bar, which represents the 3x3 convolution. To give you an idea, a 3x3 convolution is what typically a border detector would use, for example. And we could achieve almost 200 frames per second for the 3x3 convolution. All the way down, we see the 13x13 convolution. That's a big kernel. Actually, up to that sizes, it's better if you start using other filtering techniques, for example, frequency filtering, something like that. So yeah, 13x13 is a big kernel, and yet we achieve 73 frames per second, which is more than enough for real-time execution. In a similar way, processing time presents an inverse behavior as the frame rate, so that's expected. Again, this was run on the TX2 board. So here on the left, we have the CPU that was loaded while GstCUDA was running, and we have on the right the GPU usage. As it is expected, the CPU remains constant with every different kernel size. That's expected because everything's being run on the GPU. On the other hand, the GPU gets loaded as the kernel increases, as we expect, right? So now we want to change our test conditions a bit. We don't want to test compute capabilities, but we want to test data transfer, the data throughput that GstCUDA may offer. So for that, we developed a simple memory copy kernel. It just takes the input pixel and assigns it to the output pixel. So that way, we can stress data transfer, again, in the TX2, using our Cudafilter element, and again, the unified memory allocator. So this is the maximum frame rate we could achieve. As you can see, we present both the not in place and in place if you want to see the data later on the presentation. But for 4K, we are able to achieve 135 and 165 frames per second. And starting from there, we kind of limit ourselves to 245. And that's because the camera we were using just gave us a 245. So we could go way above that, but we got a hardware limitation. So similarly to that, we can see processing time behaving in an inverse way as the frame rate. If you pay close attention to those numbers, you can see that the processing time is or would allow for higher frame rates, which we don't achieve. And what that makes us, the conclusion of that is that GstCUDA is not the main bottleneck in the pipeline. There are other elements involved that are being the bottleneck in the pipeline. There are hardware components. There is the NV camera daemon over there. There is a converter. So GstCUDA is not being the bottleneck right now. Again, the CPU load stats and the GPU load stats. In this case, we are dependent on the image image size. So for the sake of time and to be able to present the demo, I'm gonna go through this real quick. This was our last test, which I very much rather present the demo. So what we want to show you is actually one of the algorithms that we developed to test this real quick. This is using our Cudafilter quick prototyping element. So, and this is the GStreamer launch pipeline. This is all you need to run. Can we switch the screen, please? Thank you.
As you can see here, we are applying a border enhancement filter that is running at 180p, 60 frames per second. Below, you can see the CPU load and the GPU load of this example. Here is the camera that is running on a Jetson TX2, configured in its maximum performance mode.
I think we can leave it while we go through the question and answers.
Yeah.
We're ready for Q&A?
Yeah.
Yeah.
All right. Okay, thank you, everyone. And I'm going to try to stay out of the way of that thing. I don't know what's happening. But OK. Do we have any questions?
What's the, could you compare your solutions and then to NVIDIA's DeepStream?
Mm-hmm.
The DeepStream is also based on the Gstreamer and for the video analysis.
Yes.
Thank you.
So they both serve kind of different purposes. DeepStream is for doing deep learning inference using GStreamer. DeepStream is an amazing tool. It has a very, very high efficiency. GstCUDA is not for inference. It's just for doing low-level image processing. So DeepStream is for deep learning inference. GstCUDA is for low-level image processing.
Mm-hmm. All right, next question. Somebody? Question? Questions about the performance data? So, and is this where the demo ends?
Yeah.
Okay.
Yeah, we just wanted to leave these here.
Or we can change to the presentation to show you some resources.
We have a couple of minutes left if you just want to show the last few slides you had.
Yeah, we have the resources slide, or also we can give the performance statistics that we jump on.
Well, here's a few resources before you go that you may find useful. You can read much more and in much more detail about GstCUDA in our wiki, gstcuda.ridgerun.com. Also, you can contact us at ridgerun.com, and specifically ridgerun.com/contact. There's a contact form that we all receive. So any of us will start a conversation with you. If you have any question, please feel free to ask. We are more than happy to help and to customize our tools for your needs. That's our main goal, right? So I appreciate everyone coming in here tonight.